Welcome to another week. We're in the middle of finishing up the last proof of a theorem, part 4, which is a very important theorem, the theorem that has some of the most basic properties of limits we want to use, meaning that the limit of a constant times a sequence, we can take the constant out, that the limit of a sum of two sequences is the sum of the corresponding limits. The limit of a product is the product of the corresponding limits, and we were doing the limit of the quotient, and for that we saw that it was enough to do the limit of 1 over b to the n. So let me go to the page and remind you where exactly we were working at the time, trying to prove that if Bn is a sequence that approaches b is not 0, then the limit of the reciprocal of 1 over Bn is exactly 1 over the reciprocal of the limit. And this is a little explanation of that, how that would be enough to show the quotient, because then you can think of this as the product of a times 1 over b to the n, and use the product property that we learned before, and then use this last property that we are yet to prove, right? Then we were at the discovery point of our proof. So we said, okay, this is what we want. We want to make this smaller than epsilon, for an arbitrary epsilon, whenever n is big enough. So find a capital N that would make this work. And then first thing we did is we put a common denominator here and separated all of the quantities involved, like so. And then we said, we thought about what are the things we can control and what are the things we need to still pursue. Now, this over b, that's not a problem. It's a constant. So in the end, when we choose our epsilon prime, we can choose it appropriately so that we deal with this constant. This b minus bn, we can control. That's the part that we can make as small as we want. So that's great. And then the problem we found is this bn. This bn in the denominator is troublesome because we don't want it to be 0. If it's 0 or close to 0, that's a problem because that makes this number big. And if this number is big, we cannot make it as small as epsilon. So we were thinking, how can we fix that? And what we realized is that because bn is approaching b, what we can do is pick a small neighborhood around b that avoids 0. And in that way, maybe we can guarantee that this bn quantity is not a problem. And so that's what we did. We used that the limit is b, and we used as our epsilon prime for now something that is less than b over 2. So we took just the distance from 0 to b, this one that you see right here, and we halved it. We use half of it to give ourselves a little bit of leeway in case we need more for something else. So we chose half of that. Okay, and then we try to see if that's enough for us to control Vn, this absolute value of Bn. And that's the last part we did. We ask ourselves if we can guarantee that Bn is bigger than something in this case, and we can. And that was the argument. We wrote b. This time it's a little bit different. We have to start with b, and we wrote it as b minus bn plus bn. So put a 0 here. Use the triangle inequality here to separate into these two pieces. Write down what we can to control this first piece, which is less than epsilon prime. It's right here on top. And epsilon prime is in turn less than b over 2. So we write b over 2 here. And the other we keep. And then from this, in the end, we subtracted b, absolute value of b over 2, both sides. We got this one, and which finally gives us this lower bound for Vn, which if you think a little bit, we can rewrite as follows. We can write it as 1 over Vn is in fact less than 2 over b, right? And this is precisely what we need. Let me take you back to where we were. We were right here, yes, in the parts that we want to control. So this will be useful because now this part over here, the 1 over Bn, we can control with 2 over b, right? So then let me write over here. So then it would be enough to show b minus b over n. So, okay, this one is less than, I'm going to use this one, as less than 2, and then there's going to be 2 b's here. So it will be a quantity b squared. And then it would be enough for us to show this one. If we make this one less than epsilon, because this one is bigger than the one we want, then the one we want will be less than epsilon as well. So it'll be enough to show this one over here. And for this, we are set, because now we can pick as our epsilon prime what we need. So we can solve for b minus bn, in other words, and this will make it so that it's epsilon quantity of b squared divided by 2, right? This is the same as this one. And then this suggests what our epsilon prime should be. So we should pick this as our epsilon prime. So this quantity over here looks to be, this should be less than or equal to our epsilon prime, right? So then our epsilon prime should be, so that, sorry, I wrote it the incorrect way. So we need to pick an epsilon prime that is even smaller than this, right? So pick epsilon prime smaller than this. Okay, and you can tell that we need epsilon prime to fulfill 2 roles. It should be smaller than this to make this work, but it should also be, if we go back to, it should also be less than the magnitude of b over 2, so that we can make this inequality over here work, right? So this is a more involved proof. You need epsilon prime to satisfy 2 things at the same time. But I think we're done now with the discovery step, and we can finally write our proof, all right? So here is now the write-up of the proof. Here we go. I mean, all of these that we did here was a discovery. So let's put a divider here, and now let us write down what the proof is going to be. So here it is. So we're assuming, let me tell you first, assume that the limit of the sequence bn is b, and b is not 0. Okay. Let epsilon greater than 0 be arbitrary. Then we set our epsilon prime. Set epsilon prime. And remember, we wanted it to fulfill 2 roles. So it has to be simultaneously smaller than this quantity, as well as the first one that we had right here on top. So a way to make, to guarantee both of those is to make it the minimum of both, right? Or smaller than the minimum of both, right? If you want strict inequality. So let's set it as set epsilon prime smaller than the minimum of quantity of b over 2, absolute value of b over 2, and epsilon times quantity of b squared divided by 2. Okay? So that way our epsilon prime can now be smaller than both of these. Perfect. So then we use this epsilon prime with our definition of limit. I'll write it here. By definition of limit, limit bn equals b using epsilon prime, there is n prime a natural number such that if little n is bigger than n prime, then bn minus b is less than epsilon prime. Correct? All right, and then it's just a matter of rewrite our proof, all the steps that we did in our discovery step in the correct order, right? So first we need to establish that Vn is not too small. And the way we did it is by using that epsilon prime is less than b over 2. So let's write down that step. Then the absolute value of b, I'm just copying what we did before. That's why it looks seamless right now. This is b minus bn plus bn, which by triangle inequality is less than b minus bn plus absolute value of bn, which by this inequality is less than epsilon prime plus absolute value of bn. But epsilon prime is smaller than the first one over here. So this is smaller than b over 2 plus absolute value of bn. And then putting the first and the last together says that Vn is greater than b minus b over 2, which is b over 2. So 1 over bn is smaller than 2 over b. And we're going to keep this inequality, right? We're going to use it later on. Okay. Then now we go and write down what we want. So finally, I think we can now make it work. Finally, 1 over b, bn, minus 1 over b, which is what we really want. Well, that's the same as b minus bn over b bn when you do the common denominator, which if we separate it is less than b minus bn over absolute value of b times bn, which by this inequality over here, so let me give this, call it 1. So this is less than by 1 b minus bn 2b squared, right? This b multiplies that b, becomes b squared. And then this is less than, by our original assumption, this b minus bn is less than epsilon prime. So this is now 2 over b squared epsilon prime. But what will we say about epsilon prime? We can still see it here. Epsilon prime is smaller than this quantity, epsilon capital B squared divided by 2. So then this is in turn less than 2 over quantity of B squared times epsilon B squared divided by 2. And we made it so that everything cancels here and it looks pretty, right? So these numbers cancel. And all we are left with is epsilon. So we're done, right? So I should probably say for n bigger than n prime, this happens. So we are done. We found the capital N that makes it work. The capital N that makes it work is the same capital N, it's the N prime that makes this limit work with this epsilon prime, with this number epsilon prime. So for numbers bigger than that capital N prime, this difference is indeed smaller than epsilon, right? I mean, this is epsilon at the very end. And that's the end of my proof. All right. Like I said before, last class is probably the hardest one, right? Because it involves combining. Well, the product was tricky as well. See, the good thing about this is that now we could use these properties to do all sorts of limits, right? And many of them are in your homework. Like now you can do the limit of a polynomial, right? Or the limit of a rational function, right? A sequence that is given as a rational function, we can now quickly do it. So, I mean, like I said before in this class, we don't quite do many of those things because that's what you did in your regular calculus class, right? So I'll just give it as a small example here. So example, see what would be this limit if we wanted to do, say, what is the limit of what is it that I want? Let me think. Let's do okay, suppose the limit of an is 3. And now you want to do what is the limit of an to the cube plus 3an squared plus 5 divided by an plus 7, right? Well, by the first property, the last property we saw, we know that the limit of a quotient is a quotient of the limits. So we can break this into these. Further, but the limit of a sum is the sum of the limits. So you can now divide this into these smaller ones, an cubed, 3an, and 5 divided by an and 7. Now further, you can take the 3 out, this 3 out as a constant, we can take it out. And this an cube is like an multiplied with itself 3 times. So you can use the product property 3 times. And what you're going to get is the limit of an to the third plus 3 times the limit of an plus the limit of 5 divided by the limit of an plus the limit of 7. And finally, we can now do it, right? Because we, by assumption, this limit of the sequence an is 3. So we get 3 cubed plus 3 times 3 plus the limit of a constant sequence is the number itself. Professor. We learned that before as well. And so this is 3 plus 7. And whatever this number is, let's see, it's 27 plus 9 plus 5 divided by 10. That's going to be our answer, right? 32 plus 9. That's 41 tenths, right? A little example of how those properties are actually quite useful to do now the limits of a whole bunch of sequences. All right. Next order of business is this other theorem, theorem 2.3.4, which is called the order limit theorem. And it will be also quite important, right? How is the order among real numbers preserved or not, depending on the limits? And it turns out that it is preserved. So this is what it says. It says, assume the limit of the sequence an is a, and the limit of the sequence bn is b. Part 1. If it turns out that an is positive for all n, then the value of the limit is positive too. Number 2, if the sequence an is smaller than the sequence bn, then that inequality is preserved when you take limits. And a little particular case of the previous one, if you think about it a little bit, if there is some constant for which c is less than or equal bn for n in n, then c is less than or equal b. And similarly, if an is less than or equal c for all n, then a is less than or equal c. All right? So in other words, limits are preserved, inequalities are preserved by limits. So if you have a sequence that is smaller than another one and you take limits on both sides, that inequality is preserved, right? You still get that the first limit is less than or equal the second one. Okay, and this one is actually easier than the previous one we did. In fact, we only really need to prove the first part, and I'm going to show you why. It's actually quite straightforward to see how the other two parts follow from the first one. So, but let's go in order. So how could we prove the first part? Well, it would remember, we're just going to use the definition. Limit of an equals a means that if I pick a little neighborhood around a, eventually everybody is in there, right? So picture time. Here's the real line, and somewhere there is a. This time I'm gonna need 0 as well, because in this case we know that a is positive, right? I mean the an's are positive. So let's suppose that that the opposite of what we want happens, right? Let's suppose that a is negative, right? See, this, we want to prove that a is positive. So let's suppose not. Let's suppose that a is negative, right? But then think about it. What is the definition of limit? The definition of limit is that if I pick any neighborhood around a, eventually everyone is in that neighborhood, right? So how can I get a contradiction from here? Well, easy, just pick a small neighborhood, right? If I pick, say, this neighborhood that I just drew here, Imagine now the situation with the sequence an. See, how could this be? On the one hand, the sequence has to be positive, meaning all the elements are in here, to the right of 0. Yeah? On the other hand, eventually, all the numbers have to be in here. That's impossible, right? You cannot have numbers that are simultaneously here, right? I mean, at the beginning, maybe no problem, right? They're over here, the a's. I don't know. But eventually, the a's need to jump in here, right? They need to be inside this neighborhood. And the moment they do that, we're going to have a problem, because we're going to have numbers that are obviously less than 0, because they're to the left of 0, right? That's the idea of the proof. As you can tell, it's actually quite simple. So let's just now write it down. What is it that we need to do? Well, first we assume A is negative, right? So here's the proof. Suppose that A is negative. Then we need to pick this epsilon, right? How big of a neighborhood are we gonna pick around A? And don't pick it too large. If you pick it too large, the argument is not gonna work, right? If I make it really big so that I include 0, then I can make it work. I can make it so that all the numbers are over here, and there's not gonna be any contradiction. So to have a contradiction, we need this epsilon to be smaller than the distance from A to 0. So let's just pick that, right? So let epsilon be the magnitude of A. So I'm actually picking one that is a little bit bigger than my drawing, but it's not gonna matter. I mean, if you want, you can pick this divided by 2. Anything smaller will work, all right? So then, by definition, there is some capital N, a natural number, such that an minus a is smaller than epsilon. Remember, that's absolute value of a, whenever little n is bigger than capital N, right? And then all we need to do now is show that this is a contradiction. And what is the contradiction we want to get? The contradiction we want to get is that an is going to be negative, right? So how are we going to do that? Well, here is how. Look at the following. What is an minus a? Well, on the one hand, I don't know what this number is, but for sure that number is less than or equal an minus a, right? Any number is always less than or equal its absolute value. That works in general, because the absolute values is either the same, if they have, if both of them are positive, or if this guy is negative, then this number is obviously bigger because this is positive, right? So this inequality should be clear to all of you, right? But now I'm gonna tack this other inequality over here. So we know that this is less than absolute value of a, right? And here is now where we finish the argument. What is absolute value of a? What is the absolute value of a negative number? Because a is negative, right? What is the absolute value of a negative number?
It's opposite, so negative a.
Anyone? The absolute value of a is equal to?
A.
No, negative a.
Negative a. Because a is less than 0.
Oh, probably I can't hear you because, okay, probably someone said it and then my volume was down, I guess. What's the absolute value of a?
Negative a?
Yeah, negative a, right? And then we're done, right? Because we can cancel negative a from both sides of this inequality, and this now says an is then less than 0. And that's a contradiction, right? Because we said that that all the an's were positive, right? Let's look back in here. It said that all the an's are greater than or equal to 0, all of them. And this is not good. If little n is bigger than capital N, then these are negative. So I'm just right here for n little than capital N, little n bigger than capital N. This will happen, which is a contradiction. And we're done. right? Contradiction to what? Well, that we assume A is less than 0. So it must then happen that A is in fact greater than or equal to 0, the opposite, right? Now, a little remark here. We actually proved more. I don't know if you realized. See, if we look at our assumption says that all the ANs are positive. And we don't need that. We don't need that all of them are positive. What we need is that all of them are eventually positive, right? See, I don't care if the first 10 are negative, because my contradiction over here was that I can find n's that are really big, that are all the, rather, my contradiction was that all the n's that are sufficiently big are negative, right? So the assumption could be if the ANs are, if there is an infinitely many number of ANs that are positive, then the limit will be positive. So we don't need all of them to be positive. See, it would be enough if eventually all of them are positive, right? If after some point all of them are positive, we get the same contradiction. So that's the first remark. The second remark is that now to do the second part, we can do this really easy trick. We can consider the difference sequence, all right? So now let's try to prove the second one, and I'll show you how quick we can do that. So this was the proof of 1. So to prove 2, we don't need to do a lot of work. We simply can do, we could do the following. So we are gonna create a new sequence, the sequence Cn, which will be the difference, Bn minus An. So notice that Cn is always positive, because why is that? Well, because our assumption was that Bn is greater than or equal An, or An is smaller than or equal Bn, less than or equal Bn. So that means this difference is always positive, right? The B is greater than the corresponding A. So this is positive. So that means all of these elements in the sequence are positive. Well, that means that we can use part 1. So by part 1, the limit of Cn has to be positive, right? But what is the limit of Cn? Well, it's the limit of the difference of two sequences. So by the previous theorem, by the algebraic limit theorem, we know that the limit of the Cn is the limit of Bn minus An, which is in fact the limit of Bn minus the limit of An, right? So this has to be positive, and then we're done because this is B and this is A. So this implies that B minus A is positive, which implies that B is greater than or equal A. And that was exactly what we wanted to prove, right? So that's the end of that one. Like I said, it's super easy. And the third one is easy as well, because for the third one, all you need to do is use a constant sequence. So for the first one, Bn is greater than or equal to C, so you can use the constant sequence C. So pick An equals C all the time. C, 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 C. And then by the previous part, we know that A is less than or equal to B, but the limit of a constant sequence has to be the constant itself. All right? I'll write a sentence just so I don't leave you hanging here, but it's really that easy. So for part number 3, let An be C for all n. Then by part 2, the limit of the An is less than or equal than the limit of the Bn, but this is B and this is C. And we're done. And that's for the first part. And for the second part, well, we do the other one. Let Bn be C for all n. Then by part 2, the limit of An is less than or equal than the limit of Bn. This is a constant sequence, so this is C, and this is A. So then A is less than or equal C. And we are done with the order limit theorem. All right. Questions so far? Good. So we'll now move up to the next section. We're a little bit behind with respect to our schedule. We should have finished this one last time, but I obviously did not realize that this was going to require a bit more of an explanation, but that's all right. We're doing okay. So this next section, 2.4, is we're going to look at the monotone convergence theorem. That's an important one. And then use that one to start talking about series, right? So we'll start with a definition, important definition here. Definition 2.4.1. And we're going to define what it means for a sequence to be increasing or decreasing. So in our book, a sequence, AN, is increasing if AN is less than or equal AN plus 1 for all n in the natural numbers. Now, I on purposely said in our book because you'll notice that it allows the possibility of equality, right? In other books, they call it for when they say increasing, they want strict. In our book, we don't want strict, and there is no, we haven't, mathematicians agreed upon that word. So it's okay, as long as you understand if equality is not included or it is included, then there's usually no confusion. All right, and it is decreasing if the opposite inequality happens. If AN is greater than or equal AN plus 1 for all n in n. And then, so these are the new words we learned, increasing and decreasing, although, of course, you knew them already from before. And then this one, maybe you didn't, or you forgot. A sequence is monotone if it is either increasing or decreasing. Okay, and obviously, there is a reason why we pick those names, right? I mean, how do you picture an increasing sequence? Here's one. So you have A1, and then A2 has to go to the right, and then A3, and then A4. Then maybe it stays there for A5 and A6, and then maybe it keeps going. Maybe big jump for A9, but then maybe it stays there, and then it keeps going, A11, and so on, right?
Professor?
Yes.
Well, they could both be equal, but then it says it's increasing if it's less than or equal to, or decreasing if it's greater than or equal to. Does that mean that it could be both?
It could be both, yeah. If it's a constant sequence, right? If it stays the same all the time, like the sequence 5, 5, 5, 5, 5, 5, that one is both increasing and decreasing, right? According to our definition. I know it seems kind of weird, but yes, it can happen.
Okay.
Mm-hmm. Right, and I was illustrating why we call them monotone because they're sort of not very interesting, right? I mean, they keep always moving to the right, monotonically, right? Or, I mean, this was increasing. If to look at an example where it is decreasing, it would be look at it in the mirror, right? Instead of going to the right, we're going to the left, okay? And the reason these sequences are important is because we can actually guarantee that these sequences are convergent, right? If we have another property. So here is the theorem. Theorem 2.4.2 has a name. It's called the Monotone Convergence Theorem. And you probably heard it mentioned when you took calculus. I certainly talk about it in my first semester calculus class, but I mean, I cannot prove it at that point. I don't have the tools necessary to prove it. So we just mention it and argue why it's, I mean, wave my hands a little bit and explain why we should expect it to be true, but I cannot really prove it. But now we can. That's the greatest thing, right? So here's what it says. It says if a sequence is monotone and bounded, then it converges. Really awesome, right? Every time you have a sequence that is monotone and bounded, it will be convergent. So if we go back to my little example here, these numbers that I was drawing either keep going all the way to infinity, right? Keep increasing. That would mean it's not bounded. Or if it is bounded, if over here suddenly there's a bound, call it M. That's a bound. So my sequence will not pass this letter M. Then eventually these numbers need to start accumulating near M. The sequence will be convergent to a number either M or before, right? It could happen before. All right. So let's prove this. How do we prove this? Proof. And the hardest part about this proof is to actually try to come up with what the limit should be, right? Once we realize what the limit is, the proof is actually very, very straightforward, right? So let's start writing our assumptions. So let's say let AN be a monotone and bounded sequence. Now, I don't want to repeat the argument twice, and it will be the same argument, right? If it's increasing or if it's decreasing. So we're just going to pick one of them. So I'm going to pick the increasing case. The other one is similar. So assume AN is increasing. If you want to do the other one, just reflect in the mirror every one of my arguments. All right. Okay. So let's assume it's increasing, and we're going to consider this set. And that will probably give you a clue of what the limit could be. The set will be the ANs. So it's just the sequence, really. But I'm writing it as a set to give you an idea of where we're heading, right? What do we know about this set? Well, it's non-empty, of course, right? Because A1 is in there, and A2 is in there, and A3 is in there. It has a lot of elements, right? So it's non-empty for sure. Well, maybe some of them are repeated, right? I actually cannot say that it's infinite, because maybe a lot of the ANs are the same, right? Like one of you mentioned before, if this sequence is constant, then this set only has one element. But for sure, it has at least one element, right? So I'm going to say clearly A is non-empty. For example, A1 belongs to A, right? And it's also bounded, right? Why? Well, by definition, if the sequence is bounded, that means the set itself is bounded, because the set is the sequence, right? The set is the elements of the sequence. So clearly A is a non-empty, and by assumption, A is bounded. Okay, and what do we know about non-empty bounded sets?
They have a supremum.
You bet, right? They have a supremum. And that guy kind of looks like a prime candidate to be the limit, no? I mean, let's go back to my drawing. So if you look at these AIs, and they're all increasing. So they're becoming bigger and bigger and bigger and bigger, but this is bounded. So which number do I like for the limit? Well, I like the supremum to be the limit, right? So that's the hardest part of the proof, thinking that the limit has to be the supremum. So by the axiom of completeness, A has a supremum. let's give it a name. Let S be the supremum of A. And now what we want to show is that S is the limit. We will prove that S is the limit of AN. That's our goal. All right. Let's move it up right here. Okay. How do we do that? Well, we do it according to the definition, right? We pick an arbitrary epsilon and we show that we can make the AN and the S be within epsilon for n sufficiently large, right? So that's what we're going to do. And here's how we're going to do it. It's actually quite easy. So we start by picking an epsilon. So let epsilon greater than 0 be arbitrary, right? Now, what we're going to use our famous lemma 1.3.8, the one that characterizes the supremum. Remember that? That lemma said that if you take the supremum and you move a little bit to the left, you surpass an element of the set, right? So by lemma 1.3.8, there is AN in A such that AN minus A, so is, let me write it, okay, picture time. So just like we said, so we have the supremum, S, and we're moving a little epsilon to the left. So that's S minus epsilon. And when we do that, we capture an element that's to the right. So such that S minus epsilon is less than AN. That's the consequence we want. All right. And okay, so we know this happens. And I'm going to give it a different name. Instead of calling it AN, let me call it a capital N. You'll notice in a moment. I mean, I can call it whatever I want, but you'll notice in a moment why I'm calling it A subcapital N. Why am I calling it A subcapital N? Well, because I'm going to now use the fact that the function is increasing, right? So because the function is increasing, the sequence is increasing, that's what I meant, because AN is increasing, then if little n is bigger than capital N, this happens. The AN is even bigger, right? If you pick an even bigger index, then the sequence keeps growing, right? It becomes greater or equal. So maybe it stays the same, but it's for sure greater than or equal, right? So this happens, but then in the same way, we know this is true. So this is less than S minus epsilon, right? So then what I want to look at is, remember what we're after. We want to show that the limit is S. So what we really want to do is to check the distance from S to AN. So let's do that. What is S minus AN? Okay. Now first, notice the following. S is an upper bound of the ANs, right? So let me, because S is an upper bound, you can see an upper bound of A, then we know that this happens, right? AN is smaller than S. S is an upper bound. S has to be bigger. And the reason I'm writing this, because this is the same as S minus AN is positive. That's important, because then these absolute value bars are not needed. I can simply write S minus AN, because this number is positive, right? That's what I'm writing here. Yes? And then I can use this inequality that I have over here, right? What happens when you subtract AN and add epsilon on the other side? You get S minus AN less than epsilon, correct? So that inequality I'm gonna now type here, and we're done, right? We are done. What did we prove? We started with the sequence. Using the supremum, we defined the supremum. We use this lemma 1.3.8 in the supremum for a given epsilon to find out the capital N that is in here. Then that A sub capital N, that capital N is the one we're going to use. If we find anything bigger than that capital N, then this inequality happens. And then that implies that S minus AN is smaller than epsilon. And S minus AN happens to be the same as, it's a positive number because S is an upper bound of AN. So this is the same as the absolute value of S minus AN. And because they are the same, I just show that for little n bigger than capital N, this distance is less than epsilon. So this means that the limit of AN is S. And that's it, right? So this sequence will be convergent. Every time you have a monotone sequence, one that is increasing little by little but is bounded, it will be convergent. So awesome. All right. Now we'll use this to talk about series, right? At least series where the terms are positive. You'll see in a moment how we can do that. So first, let's define what a series is. So this will be definition. (2.4.3), and it's called convergence of a series. Okay, so here we go. Let Bn be a sequence. An infinite sum, an infinite series, is a formal expression of the form, that's how it looks like, capital Greek letter sigma from n equals 1 to infinity of Bn, and it's meant to represent these, right? B1 plus B2 plus B3 dot 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 plus Bn, and add all of them, right? Now you'll notice I wrote formal expression because now I'm gonna define it. We're gonna really define its meaning, and this is important, otherwise we get these crazy things we talked about at the beginning of the chapter, like things that add up to two different things, right? So we define the corresponding sequence of partial sums S sub m by, and these are not too bad, Sm is B1 plus B2 all the way to Bm. So in sigma notation is Bk from 1 to m. So that's a sum that we can really figure out, right? And we say that the infinite series Bn converges to the number B, capital B, if the sequence Sm converges to B. And we write it like this. We write that the sum of the Bn's equals B, right? Okay, so we'll do a few examples and then a nice criterion to check for many series. So the first one is one that you probably have seen. For sure, you should have seen it. So it's going to be the sum of the reciprocals of the squares. So
sorry, Professor, can you put the paper down a little?
Sure.
Thank you.
So here's our first example, the sum of 1 over n squared. So this is 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25th. And if you remember your calculus days, you know that this guy is actually convergent, right? Now, we're doing things here differently in this class, because if you go back and think about, well, how did we know it was convergent? Well, there was something called the p-series, right? And how did we figure out what the p-series was? How did it work? Well, it came from the integral test. Okay, and the integral test, well, for that you need an integral, and we haven't even talked about derivatives in this class here. So that's not going to be the way, right? So we're not going to do it that way, because we're not going to do the p-series based on the integral test, because integration will come at the very end of the semester. So that's not going to be our approach. So let's make sense. So by the way, it's actually a hard thing to know what the answer to this series is, right? I don't know if you've ever seen it. There are elementary proofs that are actually quite challenging, and in my I go over the answer of this one in my complex analysis class 655. One way of knowing, right, which is not elementary at all, and it's a challenging thing, right? This actually converges to 6 over pi squared, believe it or not. 6 over pi squared. Now we're not gonna. Sorry, pi squared over 6. I don't know why I flipped it. Pi squared over 6 is the answer to this one. Pi squared over 6. But that's not what is important right now. What we want to know is, why is it convergent, right? Why is it convergent? That's really our question. And the way we're going to figure it out is, we're going to try to use the previous theorem we learned, that if we have a sequence that is monotone and bounded, then it's convergent, right? So to show this is convergent, we should show that its partial sums, the sequence of partial sums, is convergent. So to show the series is convergent, we need to show that the sequence of partial sums is convergent, right? That's all we need to do. Now, well, and how can we do that? Well, let's take a look at the sequence of partial sums, right? What is S1? S1 is just 1, right? Then S2 is 1 plus 1/4. How about S3? Well, it's 1 plus 1/4 plus 1/9. And then S4, 1 plus 1/4 plus 1/9 plus 1/16. And so on, right? Now, would you say that this sequence is monotone?
You keep adding positive numbers to it, so it keeps increasing.
Yeah, that's exactly right, correct? As long as we keep adding more stuff, which we are, right? We're adding positive things. That's the important thing here, right? This is only going to work out if your series is made up of positive terms. Because then every time you're adding a new term, you're making it bigger, right? The partial sum is becoming bigger. Look here. First is 1, then is 1 plus a little bit more, 1/4. Then is what we had before, 1 plus 1/4, plus a little bit more, plus 1/9. So, of course, so let me put it here, clearly, S1 is less than S2, which is less than S3, etc., right? These are all getting bigger and bigger. So it is, it's not only monotone, it is increasing. I'm going to write here, i.e., the sequence Sn is increasing. Okay, So that's half the work, right? We already know it's increasing. So what do we need to show that it is convergent based on the theorem we learned before? All we need to show is if it's bounded, right? If we have and this applies, by the way, to any series. It's not only to this 1 over n squared. If you have a series of positive terms, the sequence of partial sums will be increasing. And so to show that it is convergent, all you need to do is to then prove that it is bounded. If you prove it's bounded, then by the monotone convergence theorem, the sequence of partial sums will be convergent. So all we need to do, all we need to do is to show Sn is bounded. And this can be tricky, okay? I agree. In here, actually, we're gonna show it with a very neat trick. You'll see how we can do it. See, here's Sm. I'm gonna write it here, is 1 over 1 square plus 1 over 2 square, 3 square, all the way to 1 over m square, right? Now, I'm gonna write it as follows. I'm gonna write it, the first one I'm gonna just leave 1. And then this guy, I'm gonna write it as 1 over 2 times 2, and 1 over 3 times 3, and then 1 over 4 times 4, dot, 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 1 over m times m. And I'll tell you in a moment why am I doing this. The reason I'm doing this is because I'm gonna use an inequality, right? I'm gonna say that this is less than, and I hope you agree with this inequality. This is less than, the first term I'm gonna not do anything, but then on the next term, I'm gonna change one of these 2's by a 1. So I'm gonna write it as 2 times 1. And then the next one, I'm gonna change one of these 3's to a 2. So it will be 2 times 3. And then 3 times 4, and so on. And the last one will be m minus 1 times m. So let's check. Do you agree this inequality is true? First thing, right? Why is this true?
Yeah.
Yeah, because over here, the thing that I'm adding is bigger, right? Because the number 2 times 1 is smaller than 2 times 2. So then when I do the reciprocals, this number, 1/2, will be bigger than 1/4, right? And similarly, this 1/6 will be bigger than 1/9, and so on, right? So term by term, this one is bigger than that. The third term is bigger than the third. The fourth is bigger than the fourth, etc., right? So this inequality is true. Now, that should not give you trouble. The part that should give you trouble is why the heck am I doing this, right? I mean, how is this helpful? I mean, this still looks difficult. How can we bound this? Well, and this is where it gets nice, because it turns out that this one, we can sort of see what it is, because it's a telescopic sum, if you think about it a little bit. See, here's what's happening. This is just 1. I'm going to leave it there. But this 1 over 2 is the same as 1 minus 1/2, right? I just wrote this 1/2 in a different way. Now, the next one, again, if you think a little bit, is 1/2 minus 1/3. And the next one is 1/3 minus 1/4, etc. The last one is 1 over n minus 1 minus 1 over m. Why? Why is that? Well, it's true, because what I'm doing here is the following. What happens when you do 1 over k minus 1 over k plus 1? You do a common denominator, right? Which will be k times k plus 1. And then this one will be k plus 1, and this one will be negative k. And when you do that, these guys will cancel. And you're going to get 1 over k times k plus 1. Correct? So what I'm doing is I'm using this in reverse. I'm starting with this one, 1 over k times k plus 1, like 3 and 4, 4 and 5, 2 and 3. And I'm changing it so that it now looks like 1/2 minus 1/3, or 1/3 minus 1/4, etc. Right? This is what I'm doing here, right? And this is awesome, because then when I add them up here, it's super easy. A lot of things cancel, right? Look, right here. Negative a half with positive a half. By. Negative a third with positive a third. Go away. Negative 1/4 with the next one that you don't see because I have dot, 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 but this one goes away. This one goes away. Everything goes away except those first two ones at the beginning and the 1/m. So all of these is just 2 minus 1/m. Neat, right? How this one we could do. And that for sure is less than 2, right? 2 minus 1/m is less than 2. So let's backtrack and see what we just argued here. I started with an arbitrary SM. I wrote it here. I show you that this is even smaller than this one. I added up this one. This one is 2 minus 1/m, and that's less than 2. So that means the original one is less than 2. That means 2 is an upper bound, right? So 2 is an upper bound for that sequence. And it's made up of positive terms, so 0 is a lower bound. So for sure, my sequence is bounded. So thus, CM is bounded by 2, right? And hence, by the monotone convergence theorem, I'm abbreviating MCT, by the monotone convergence theorem, because it's bounded and it's increasing, the consequence is that it is convergent. The sequence SM converges. And if the sequence converges, then that means the series is convergent. Now, this argument does not imply that the answer to this is 2, right? That would be wrong. That's not the answer, right? That's only the upper bound, right? The upper bound that we found. It does say that the answer to this series is less than 2. Yeah, that is a correct consequence of our argument, right? Whatever is the limit to this has to be a number less than 2. That's correct. Like I told you before, it happens to be this mysterious number pi squared over 6. Okay, let's do another example. What if we wanted to repeat this argument with the sequence, not this one that we just did, but now let's try 1/n. 1/n, same thing, right? Looks like 1/2, 1/3, 1/4, 1/5, etc. Right? Could we repeat the same argument with this one and show that it is convergent as well? What do you think? So you should already know what's the behavior of this one, right? It has a name, right? This is called a harmonic series. And how do we know, what do we know about it?
It slightly diverges.
Well, there's no thing as slight in here, right?
Sure.
It's either, but I understand what, I see what you're trying to do there. So
I
it
meant
diverges slowly. That's what you meant to say,
That's
right?
what I meant, yeah.
Yeah, very good. You are right about that. It diverges. So that means we probably cannot show it in the way we did it before, right? Now, but let me ask you something. Is this thing, when we look at the partial sums, is it going to be increasing? Are the partial sums?
Yes.
Yes.
You bet, right? The answer is yes, and you can tell, right? S1 is 1, S2 is 1 plus 1/2. Like I said before, as long as the terms are positive, doesn't matter what the series is, you definitely are going to have something that is increasing, a sequence of partial sums that will be increasing, right? So yes, it is increasing. So that means that if we were to find an upper bound, if we were to prove that it's bounded, then it would be convergent, right? But you already told me it's not convergent. That means that with this one, for sure, we should be able to show that it is not bounded, right? That's what we need to argue now. So if we were to find an upper bound for Sm, then the series would be convergent by monotone convergence theorem. But we know it's not. So that means we cannot expect to find an upper bound, right? So it means it, and now think about it. What happens with a sequence that is increasing but does not have an upper bound? If it doesn't have an upper bound, that means you cannot contain it, right? It means it keeps growing and growing and growing as big as you want. And if the sequence keeps growing and growing and growing, then it means it has no limit, right? Yeah? So at least, the point that I'm trying to make here is that thanks to the monotone convergence theorem, if you have a series made up of positive terms and you want to check convergence, all you need to check if it's bounded, if the partial sums are bounded. Because if the partial sums are bounded, then by the monotone convergence theorem, it will be convergent. And if the partial sums are not bounded, then it means it grows without bounds. It means it's going to go to infinity, right? Which means is the limit, the sequence of partial sums will not have a limit, which means the series will be divergent. So in a sense, the monotone convergence theorem makes things super easy for series with positive terms. You only need to check if the partial sums are bounded. That's all you need to do. So let's check that it doesn't happen for this one here, right? And this time the way to illustrate it is a little bit different. So this is what we're gonna do. Maybe you've seen this argument before. Here's what we're gonna do. So I'm gonna write these sums. So 1 plus 1/2, and then I'm gonna look at the next two terms, 1/3 and 1/4. And then I'm gonna take a look at the next four terms. And then I'm gonna take a look at the next 8 terms, right? And then at the next 16 terms, so it will be from here to 1/32, 16 terms, and so on. And why? Why am I doing this? Well, because, see, so let me stop right here. This will be S sub 32, right? When I take a look at the first 32 terms, is this gigantic one over here, right? So then observe the following. And I hope you agree with this. I claim that S sub 32 is greater than or equal 1 and 1/2. Those I'm going to leave it like that. And then these two, I'm going to change to, instead of adding 1/3 and 1/4, I'm going to add 1/4 and 1/4. Next, instead of adding 1/5, 1/6, 1/7, and 1/8, I'm going to add 1/8 4 times. And then instead of adding 1/9, 1/10, 1/11, etc., I'm going to add 1/16 8 times. And then in the next one, I'm going to add 1/32 16 times. Okay. Now, why is this true? Why is this new sequence, new sum, smaller than the original one? Well, it is true because 1/4 is smaller than 1/3, of course, right? And then over here, 1/8 is smaller than 1/7, and then 1/6, and 1/5. And in the next one, 1/16 is the smaller of these terms over here. So this is good. And here, 1/32 is smaller than all the members in here. So this is good, right? Yeah. And the good thing about this is that these terms are now easier to add. Look what we have here. This is 1/1/2. These are 2/4. So 2/4 is the same as 1/2. These are 4/8. So that's another 1/2. These are 8/16. So that's a 1/2. And these are 16/32s. So that's another 1/2, right? 1/2 is what I meant to write here. So altogether, this is a 1 and 1, 2, 3, 4, 5/2. So this is 1 plus 5/2, right? So I just argued that this number S sub 32 is bigger than 1 plus 5/2. That's not too big. You may say, hey, I'm not impressed, Professor. This is barely 3.5. This doesn't seem like something that goes to infinity, right? I mean, you only made it bigger than 3.5. And you're right. I mean, it's going to take me some time, but I can make it as big as you want, right? How big do you want it? Do you want it to be bigger than 1,000,000? This is what I'm going to consider now. Let's go and use S sub 2 to the power, what do I need here? 2,000,000. Right? What is that? Well, it'll be something gigantic, but what is the idea? I'm gonna keep doing this, right? I'm gonna write that this is bigger than 1 plus 1/2, then 2 1/4, right? Then 4 1/8, and then etc., right? And the last term that I'm gonna have is 2 to the 2,000,000, right? 1 over 2 to the 2,000,000. That's a lot of zeros. How many times? Uh, 2 to the 1, well, 1/2 of that, right? Half of this number. If this was 32, we have 16 terms. So if this is 2 to the 2,000,000, this number appears this many times. 1,999,999. Whoa, right? And the point is that this is 1/2, and that's 1/2, and that's 1/2, and that's 1/2, and I have 2,000,000 1/2s. So this is going to be 1 plus 1/2 plus 1/2 plus 1/2, etc. How many 1/2s? Well, over here I only had 5 because this number was 2 to the 5th. Over here I'm going to have 2,000,000 1/2s. So this is going to be 1 plus 1/2 times 2,000,000, and that's 1,000,000. So there you go. I could make it bigger than 1,000,000. This is already bigger than 1,000,001, right? Now I had to use an incredibly gigantic number of terms to the 2,000,000, right? That seems incredible. It's like, whoa, out of this world, how big this number is. But I could do it, right? So that's the point. I can make this sequence as big as you want it. You tell me how big you want it, and I tell you how to use this trick of adding up all of these terms so that it is as big as you wanted it to be. So this is going to be the end for today. But what we're going to start with next class is there's this little theorem called Cauchy's condensation test, which pretty much explains this idea in general, right? And you can now then use that idea to show that a whole bunch of other series are either convergent or divergent. So that's where we're going to pick it up next time. All right? Okay, so I'll stop right here.